For this video, we are going to look at periodic functions and a new kind of transformation of graphs called horizontal stretching and compression. So first, we're going to recognize graphs that regularly repeat themselves and give them a name. That name is going to be periodic functions, and we're going to define them not just by how their graphs look, but algebraically. And then we're going to find ways to horizontally scale the graph of a function. Stretch and compress. So a periodic function is, in some sense, a function whose graph repeats itself in a regular way. So here's an example of what might be a periodic function. So how do we tell this is periodic? Well, each bump represents a portion of the graph that repeats itself. You notice that every time you go over a bump, it repeats the same bump each time. Has the same shape and the same size, has the same height, has the same width, and each of those bumps has the exact same shape. And notice that the bumps repeat themselves every 6 units. It's kind of hard to see, but if you start at the origin, you go up one bump and to the right, it comes down again at the end of that bump at 6, and you do another one, it comes out at 12. If you go the other way, starting at the origin, it goes to -6 and then -12. And that tells us that the period of the graph is 6. The period is the horizontal length that you go when the graph starts repeating itself again. So we're going to call this function f. And the question is, 6 is the period. And so if we want to think about this algebraically, we want to look at what points look like every 6 units apart in the horizontal direction. So here's one point. This is at x equals 2, and then y is approximately 2.598. If we move 6 units to the right, that'll be at x equals 8. Notice that we get the exact same y coordinate. We're at the exact same place in the graph, in the bump, I should say, and that means we should be at the exact same y coordinate, the exact same height. And similarly, if we start at x equals -5, our y is approximately 1.5. If we move 6 units to the right, we're going to be at x equals 1. And again, since we're at the same point along that bump, we're going to be at the same y coordinate, 1.5. The basic idea is if I look at the height of the graph at any value x, and the same height at 6 units to the right, x plus 6, they're going to be exactly the same. So this is what gives us the official definition of what a periodic function is, or at least the algebraic definition. A function f is periodic if there is some number p such that f of x equals f of x plus p for all x. So in this case, the smallest positive value of p that we can possibly have is called the period of that function. And in our previous function, note that we had f of x equals f of x plus 6 for all x. So in this case, our p was 6. That tells us that f is periodic. But notice that 6 wasn't the only number that made this equation true. If we added 12 to each one as well, we also got the same y value. In this case, we're starting on one bump and then skipping a bump and going to the next bump if we're adding 12. Still going to get the same y coordinate, we just travel twice as far. So adding 12 skips a bump, but still gives the same output, still gives the same y coordinate. However, if we're looking for the smallest value that gives us a repeated pattern, then the period is 6. All right, so now we're going to move a little bit from periodic functions to horizontal scaling. However, we will use that same function f as our reference. So here's our graph of f, the one with the repeating bumps. And what happens to the graph if we replace f of x with g of x equals f of 2x? So what we're doing is we're taking our original function f of x, and instead of having the input be x and the output be f of x, now our input is x, our output is f of twice that x. So what does that do to the actual, to the function, to the graph? So we're going to go ahead and compare and contrast the graph of y equals f of x to y equals g of x. All right, so remember, g of x is f of 2x. How does it compare to y equals f of x? Well, both graphs are going to actually have the same values of y, right? They're based on the same function f. They're all outputs of the function f. So they're going to have the same outputs no matter what. So that means they're going to have the same range. And so let's see how this would actually happen. So if we wanted to get a y value f of 6, we can get that f of 6 from both y equals f of x and y equals g of x. So if we plug in x equals 6 into y equals f of x, yeah, we get f of 6, right? Because x equals 6. But if we plug in, well, not the same value. In this case, we plug in x equals 3 into g of x. Then g of x, g of 3 would be f of 2 times 3, because in this case our x is 3, and that's f of 6. We get the same y value. So even though we had a different x value, we get the same y value. But as you might have noticed, even though we get the same y values from both functions, they do not occur for the same values of x. However, as you may have noticed in that first example, there is a systematic way that we can determine the values of x that do give the same y values. So for instance, let's say we want a y value of f of a. Well, in f of x, we just plug in x equals a, right? And that would work, because for f of x, if we plug in x equals a, that gives us f of a. What about for g of x, which remember is f of 2x? How would we get a from that? Well, we'd have to just sort of adjust the x. So when we get the 2x, we'd end up with a. Well, the way we do that is plug in x equals a over 2. Because if we plugged in x equals a over 2 for g, then we're taking f of 2x, which is f of 2 times a over 2. Those 2's cancel, and we end up with f of x, or f of a, excuse me. So if x equals a works for f, x equals a over 2 gives us the same output for g. And actually, a helpful way of thinking about this is thinking of x as being time. And what this says is that it takes f a time units to get to f of a, right? So if I wanted to go from x equals 0 to x equals a and get to that f of a point, I'd have to wait a time units. However, for g, we'd only have to go to a over 2 to get to f of a, which means that g gets to the y values twice as fast as f does, right? If f takes a time units to get there, g only takes a over 2 time units to get there. So no matter how long it takes to get to f of a, we can get there half the time for g of a. So that means the graph along a given sequence of y values is twice as wide for f as it is for g. Twice as wide for f because it takes twice as long along the x-axis. As it is for g, g takes a shorter time along the x-axis. Or if you want to think it the other way around, we can think of g being half as wide as for f because it gets there in half the time. So if we're looking for the graph of f is equal to 2 of x, what do we expect? We expect it to repeat just like y equals f of x does, right? So we still expect it to be a periodic function, but we expect the bumps to be half as wide because each y coordinate, it only takes half the time to get there, so that means those bumps are going to be a lot skinnier. So remember, here is y equals f of x. If we graph y equals f of 2x, notice that those bumps get twice as skinny, but otherwise the y coordinates are the same. They're still roughly the same shape. They've just been squished a little bit. So that gives us what we call a horizontal compression of the graph of y equals f of x. If we have y equals f of x, y equals f of 2x gives us a compressed graph. Now the question becomes, well, what if we adjust it the other way? What's going to happen when we look at y equals f of 1/2 x? What's that going to look like? Well, that's one of the things that you are going to be exploring in the in-class activities. So I think of it the same way. Think of x as time, except this time, in the old days, we had, for f of 2x, it took half as long to get to each y value. Now for f of 1/2 x, how long does it take to get to each y value? You're going to ask the same type of questions. But I'm going to leave that to you to let you have fun with that. For now, you want to look for the PDF file with this video. It is called Periodic Functions and Horizontal Scaling.